All right, let's start here. I have circle C up on the board. Circle C. What I need to start quizzing you guys on is making sure we're up to date on our vocabulary. You guys don't need to copy this down anywhere. I'm just reviewing something real quick. I got circle C up there. What do I call angle ACB then in the circle? What do I call angle ACB? It is a special type of angle in the circle. We refer to it as a 23. Here we go. Luke, good morning at home. What do we refer to angle ACB as?
Central angle.
Good job, Luke. That's a central angle because the vertex is at the center. And here we go. We said that, all right, if you know the measure of a central angle, that's the same as what measure now? If you know the central angle, that's the same measure as 2/6. Emma, what's good?
The measure of the
arc. Yeah, so angle ACB would be the same measure as arc AB. We learned that on day 2. Everyone remember that? We're good? Now, here's what I'm going to throw at you. Let's say in the same circle, you have 2 central angles that are congruent. That's not what the 2 I wanted. We have 2 central angles that are congruent. So what's that mean to you guys? Jeez. What's that mean to you guys then? If those 2 are congruent, Radhika, what else? The arcs have to be congruent. Makes sense. And that's our first theorem I'm going to show you today in your notes. Is that if you have congruent central angles, the arcs have to be congruent. So let me draw a quick diagram for you, what I'm talking about. So you can take your circle right there. I'll call it circle O. AOC. I have B. And I have D. So here's what I'm going to tell you. If angle BOC is congruent to angle COD, then, so I'm telling you BOC and COD, those 2 central angles are equal. Everyone see the 2 arcs that have to be equal then. And yes, you can set arcs congruent to each other. We're going to write that in our proofs tomorrow. Then arc BC is congruent to arc CD. If the central angles are congruent, that implies the arcs are congruent. And then all number 2 is saying under theorem 1, number 2 is saying the reverse. If you have arcs that are congruent, then the central angles are equal. That's all number 2 is saying. It's the reverse. If you have congruent arcs, you have congruent central angles. Questions there about your first theorem? All right, theorem. I'm going to kind of go fast through these, and then we have a bunch of time to practice all of them. Theorem 2 involves chords. You guys remember a chord? It's a segment in a circle where the endpoints have to be on the circle, right? So chord AB. We all remember that. Diameter of chord as well? Can a diameter be called a chord? Yeah, just goes through the center. It's the longest chord, remember, too. So here's what theorem number 2 is saying. If the chords are congruent, so are the arcs. If you have 2 congruent chords, so let's put in 2 congruent chords here. AB and CD. I'll just put a little center point there. If the chords are congruent, the arcs are congruent. So in this case, if AB is congruent to CD, then the arc AB is congruent to arc CD. So if the chords are congruent, you got the arcs congruent. And the reverse, number 2 saying the reverse. Hey, if you got congruent arcs, the chords that are formed them are also congruent. Any questions so far? Right? If the angles are equal, so are the arcs. If the chords are equal, so are the arcs. Now we're going to get a little different in theorem number 3, but any questions on 1 and 2 right now? Everyone's good here, home? Okay, number 3. Now let's get a little bit different. It still involves chords. But now it's saying if you have two chords that are, ooh, big word, huh? Equidistant, the same distance from the center. So if you have two chords, in my case, everyone take CB and ED. See how they're both 8 units away from center A? If the chords are equidistant from the center, the chords are congruent. Okay, the chords are congruent. So in this case, because both are 8 units away from the center, you could say chord ED is congruent to chord CB. All right, everyone, all right, on 3. Now, this last one's a big one. Big one. We're going to use this last one a lot. Not only in proofs, but in our algebra problems, theorem 4. There it is. Here's what this bad boy says. If you have a diameter, all right, so let me draw in a diameter first. AB, diameter AB, and it is perpendicular to a chord. Ooh, there's a word we haven't heard in a while. So here's chord CD. They intersect at point E. So here we go, if AB is perpendicular to CD, perpendicular, right, which forms a right angle. Maybe we won't be told it's perpendicular. Maybe we'll see the right angle symbol. So if AB is perpendicular to CB, then AB bisects CD. But only the chord. Only the chord's getting bisected. Only the chord, not the diameter, only the chord. So anybody want to tell me what two pieces have to be equal up here then? CE congruent to ED. Correct. All right. That only happens though. The chords only get bisected if you have a diameter that's perpendicular to it. Now, ready? Take a look up here. Because it is very rare that you'll see a full diameter drawn in a circle. Very rare to use this theorem. Watch, I'm going to erase something here. Let's say I just given that. Does the theorem still apply? Yes, it does. It still applies. Ready? Let me just give you that piece. Does the theorem still apply? Yes. As long as a piece of the diameter is there, that theorem works. Okay? As long as it goes through or is coming from the center, this theorem still applies where the chord is being bisected. All right, everyone good? Because I'm going to tell you, it is very rare that we're going to see a full diameter drawn in to use this theorem. This is basically what we're going to see right here, or the rest of the radius drawn in. Okay, so you got 4 facts. Now I know you see statement. Yes, Sophia.
It said it bisects the arc too.
Correct. And I'm not. It does. So if I can, I just know we're not going to use that at all. So if you extended it out to B here, then that, yes, it would mean arc CB is congruent to arc BD. Yes, you could also use that as well. I just know we're only really going to use bisecting the chord. Bisecting the arc won't come into play. All right, so here we go. I know you guys see statements, reasons. It's not a proof. It's not a proof. All I want you to do, take what I gave you, and you start spitting out as many true facts as you can for me. And I'll help you out with the reason. All right, these are reasons we'll put in tomorrow's reasons column when we do an actual proof. So if I give you, in number 1, the 2 circles are congruent, and more importantly, if arc PR is congruent to arc SU. How do you mark congruent arcs? Same way we do congruent segments. You can just put a little hash mark on them. That's fine. So that's how I can mark congruent arcs. Okay, based on what we've already discussed today, based on, and I'm not going to write in the givens here. We'll do all that tomorrow. Based on what we've discussed today with your facts, if those two arcs are congruent, anything else congruent? Based on what we've discussed today already. If those two arcs are congruent, Radhika, one thing that's congruent.
Chord PR and chord SU.
Here you go. Chord PR has to be congruent to chord SU. And here's what I would expect you to write in the reasons column if you use that in a proof. What did you know was congruent already? What, arcs. So I'm going to start with congruent arcs. Imply, what did you tell me were congruent?
Chord.
What are PR and SU? Those are
Chord.
chords. So there's my reason. Congruent arcs imply congruent chords. I don't need anything fancy here. I just need it in the right order. So because the arcs were congruent, that implied the chords were congruent. Perfect. There should be at least one more pair up here that you can tell me are congruent. Quincy, what's up?
Well, I don't know if this would be like a proof thing, but angle Q would bisect P and R, or can we not prove that?
What do you mean? How can an angle bisect?
Or, yeah, you're right.
I thought you were on the right. When you told me angle Q, I got excited because you were on the right track.
Angle Q is congruent to angle Q.
There you go. Angle Q has to be congruent to angle T. What type of angles are those, Quincy? What do we call them?
Central.
Central. Good. And ready? We were told, same thing. Congruent arcs. That's what I was given. The arcs were congruent. Implies, that means that you have congruent central angles. What's up, Kyla?
Would QP be congruent to S or to TS?
I was going to do that myself, but since you just took it, not only those two,
And the other two.
all four are congruent. Usually, here you go, guys. Usually, let me cover this up. There you go. Usually, in a circle, all the radii are congruent. So in that first circle, QP would be congruent to QR. But since I was told the circles were congruent to each other, all the radii now are equal in both circles. Yes, because the two circles are congruent, all the radii are congruent. So QP congruent to QR, that would be true no matter what, those two being congruent. But since the two circles are congruent, all four radii now are equal.
And then wouldn't that be a congruent triangle? So you could say QPR is congruent to angle TSU.
Side, 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 side angle, side. Yep.
Would that not be the one theorem about like if chords are equidistant from something?
I don't know if they're equidistant. I'm not told if they're equidistant or not. So I only know the chords are equal because the arcs are equal in this case. My reason for the radii, ready? Congruent circles, because that's what I was given. Congruent circles imply congruent radii. And that's really, I'm going to end it there. Yes, we can say the triangles are congruent. I'll just end it there, though.
Oh, and then how would you say the other side of, like, because we know that PR, the arc PR is congruent, but the other, like, side of PR.
The major arc?
Yeah.
PR?
And then,
We could probably do a little subtraction, maybe. Say the because the circles are equal. You could say P, I would like another,
I know where it's.
yeah, 360 minus minor arc PR equals 360 minus minor arc SU, and then substitution major arc PR equals major arc SU. Yeah, you can add and subtract arcs.
If you're not given the extra, like, point, could you call it, like, major?
Mhm. Yep.
Okay.
All right, you guys are on your own for number 2 right now. Now I gave you the chord BC congruent to chord KL is equal. BC and KL, what could you come up for me? What info could you tell me?
Wait, so in these proofs, are you basically just trying to figure out? Like,
These are, don't call them proofs.
Okay.
This is just, here's given information. What can you get? What can you conclude from it? Okay, you were not ending at a point here at all. There's no destination at the end we got to get to. I just want, based on those true facts, what can you tell me is also true? All right, I'm just, as you guys keep working, just give me one thing you found so far true. 1-8. Oh, and give me one thing you found was true based on those givens.
Arc BC is congruent to arc KL.
Good job. Arc BC is congruent to arc KL. This is actually the reverse of what we talked about in number 1. Now you want to say congruent chords. Start off your reason by saying congruent chords because that's what was given. Congruent chords imply congruent arcs. All right, another fact that you know is true. Hey, now we know arcs are equal, so maybe we can use something there as well. But I'll take anything right now. 5, what do you got there? Hayden, what do you have?
CA equals LJ.
Yep, and even more, right? CA congruent to LJ, congruent to the other 2 radii as well, AB, and JK, seriously. Congruent circles imply congruent radii. And I could still look for one more here. I'm still hungry for one more thing. Remember, number 1, Owen just gave us the arcs are equal. That should automatically tell you there's something else that are equal here. One more. Come on, get hungry here. 2, 4. Emily, good morning. Anything else now that you know that arcs are equal?
Angle A is congruent to angle J.
You got it. What type of angles are those, Em?
Central angles.
You got it. Yep, be confident. You're fine. Good job. Congruent arcs imply congruent central angles. This is not writing well at all. Good enough. Everyone okay? Now we're going to hit up some algebra. Now let's hit up some algebra. Oh, I hate when he does this. Why can't we just solve the darn thing and move on? He always needs explanations. Yes, I do. Yes, I do. All right, let's take a look at number 3. I'm looking for x. By the way, if you're wondering, 8 represents the length of the entire chord. 8 is the length of the entire chord. Need a little help. Need a little help to find x. Probably going to use one of the circle theorems we've talked about here. Ooh, how am I going to get to x if 8 represents the whole chord? 8 is not the other leg. 8 is not the other leg of that right triangle. Can I get any help? Maybe a fact that you know about circles that could help you out? What's up, Sean?
Perpendicular diameters bisect chords.
Okay, I have a diameter. That's not a diameter. I discussed this earlier. You're never going to see a whole diameter. Does everybody see this piece right here that's labeled x? That's part of a diameter. So it counts towards the theorem. If it's perpendicular to a chord, what's it do to the chord again, Sean? bisects it. Correct. So each piece here will be 4 and 4. I don't know that unless I know my facts. All right, now what do you do in the solve for x? No circle facts anymore, just plain old Pythagorean theorem. Yep. I got x squared plus 4 squared equals 5 squared. So x equals 3. Now reasons, I just want whatever circle. I don't need Pythagorean theorem in there. I don't need to see the Pythagorean theorem in that box. I just want to know what circle theorem did we just use. Here you go. A diameter, or you can write the word radius. A diameter perpendicular to a chord does what? Bisects the chord. That is the circle theorem we just used here. All good? All right, take a peek at number 2. I'm going to figure out what x is there. I definitely don't have enough information to solve for x right now. I'm going to need your help finding some more info before I get to x. Anybody think they get a little help here? A little help for a kid here? Anybody at home? A little help for a kid here? Anything else true about that diagram?
The other side of the triangle would be 6.
Is it? Is it? The other leg is 6. Why is that?
They're both radii.
There we go. Yes. I know the other leg is 6, not because it looks like it, but because all, well, I can't say all radii are congruent because that's very, very false, right? In a circle, all radii are congruent. Okay, in a circle, all the radii are congruent. And then, yes, you guys know now we can use Pythag. I was kicking myself this morning because I left in the directions nearest 10th. I shouldn't be we should not be leaving this to the nearest 10th in an honors class. What should my directions have been? Simplest. Radical form, yes. Simplest. All right, but hey, I made it's not a mistake, but I'll keep to my word. I'll keep following the directions. I won't change them last minute. Take the score. Oh, God. Oh, my heart. And I'm doing this. 8.5. Good. It's a good one to break down, too. Any issues before we get to this last one and wrap it up? Anybody at home? We're all good? All right, there's a lot that goes into number 5. Now, I understand. You look at it and you're like, oh, x is 3, done. All right, that's because you look at it. Why, though? You got to explain to me why other than, oh, they look like they're 3 and 3. Yeah, you're right. Look, I'll just put it down right now. X equals 3. Great job. All right, you're right. How do I get to that point, though? First, how can you tell what the length of this chord is right here? How can I tell what the length of this chord is, Kyle?
The 2 chords are equidistant from the center.
Everybody see, perfect. 2 chords are equidistant. They're both 7 units from the center. So you have a theorem that says if 2 chords are equidistant from the center, they are congruent. So meaning this chord here is 6. So I might as well get that theorem down because there's going to be another one I need to use. 2 chords, or just chords. Doesn't have to be 2. It can be any amount. Chords equidistant from the center are congruent. All right, so that I understand that now. That's why that chord is 6. But why is each piece 3 and 3 then? Radhika, go. What other theorem do I need?
A piece of a diameter bisects the chord. Or wait, it's
Hmm.
perpendicular to it.
There, I need a perpendicular, right? So a diameter or radius perpendicular to a chord bisects the chord. All good? Okay. That's all you're going to do is some algebra. I don't even think tonight you have to explain. You just got to do the algebra. Tomorrow, yes, proofs are back in the house. They're not going to be too bad, though, so don't worry. Get a good night's sleep. You guys at home, I'll see you guys tomorrow. Hop on after school if you need any work with me.
You want me to just-
Yes, please. Yep.
I